So let's call this first part of the solution. We only look at position 1 to position 2. This is a pure work energy equation, work energy problem. And at position 1, we have that particle P. We're dropped all the way, all the potential energy from that particle P will be converted to a kinetic energy at position 2, right? So that's a work energy equation. Let's follow all the steps. First, let's draw the free body diagram for this particle P. This particle P should have a weight force that's called WP. What other forces should be on this particle? The rod is smooth, so we don't have any friction force. But there's one more force which is holding the particle. That's the normal force. The normal force N here, it's a force always perpendicular to the track. Let's imagine at this position, this is our track. So that normal force should be normal to the track. And the direction of that normal force is changing all the time because we have that curve. But in this problem, it doesn't matter since it's always perpendicular to the motion of that particle. So this is a free body diagram. Next, we can look at building all the tables. So here I skipped some of the steps to save time, but in work energy problems, we always want to build tables for kinetic energies. Okay. But before we do that, I have a question. In this problem, I only have that particle P in my free body diagram. Do I need to include particle, no, not particle, block A, our free body diagram? No. Yes, we do have a particle block A, but we're only look at position 1 to 2. It has nothing to do with that block A. Between 1 to 2, we only have that particle P. So therefore, that's a single mass work energy problem. The kinetic energy equals just 1/2 mv squared, right? At position 1, it's released from rest, 0 potential energy, 0 kinetic energy. At position 2, we have 1/2 mp vp2 squared. That's a speed of particle P at position 2. That's the first table. The second table is about potential energy. V1, V2. Here we have the weight force acting on P. That's our first type of potential energy. And before we do kinetic potential energy, we want to go back to our sketch to define where's the 0 reference point. In this case, let's agree this level is our 0 reference. So at position 2, we have 0 potential energy. That means at position 1, this particle has potential energy. If this height, let's call that h, equals 10 feet. Let's finish that table. So at position 1, we have mpgh. That's the potential energy. At position 2, that's our 0 reference level, 0 potential energy. And since we don't have any springs from position 1 to 2, so we don't have to worry about another type of potential energy. The last table here, it's a force from 1 to 2, work done from non-conservative forces. In our free body diagram, we only have that normal force, which is the reaction force. That's the only non-conservative force. But since it's perpendicular to the motion of the particle, there's no work done by that force. Okay, now we have three tables. Apply work energy equation. And work energy equation, T2 plus V2 equals T1 plus V1 plus work done from non-conservative forces. If you substitute everything, you will realize that Vp2, particle P, speed of particle P at position 2, it's the only unknown in that equation. We can solve that. That is square root 2gh. That's the speed of that particle at position 2. Okay, now we're done. That's all we need to know. We want to know the speed of particle P at position 2. We're done with the first step. Now let's look at the second step. Now we need to analyze position 2 all the way to position 3. So that's the impact problem. Let's sketch that impact problem. Remember, in the impact problem, we have a new coordinate system, T and N. Which direction is T? Use your finger, show me which direction is T. Okay, so the vertical direction, what's the name of T? Plane of contact. T, that's plane of contact. Another direction is N. N is a line of impact. Tn. So now it's a pure impact problem. We know the speed of particle P right before impact. This is P, this is A. And block A is at rest right before impact. So we know the speed of P and A before impact. We want to solve what is the speed for P and A right after impact. So this is an impact problem. We can apply the 4 equations we learned from impact problems, right? And remember the 4 equations? The first equation, it's when you only look at one particle from that impact problem, then apply conservation of momentum on T direction, you get that first equation. The second equation is you look at another particle, just only look at that particle, apply conservation of momentum, you get another equation. The third equation is when we look at both particles as a system, we can apply conservation of momentum on both T and N direction. And the third equation, it's on the conservation of momentum on N direction. What's the last equation? Anybody remember what's the last equation we learned from impact problems? Coefficient of restitution. That's the 4th equation. Okay, in this problem, since we only care about velocities on N direction, we want to find out what is the velocity for P and A after impact. So the third equation, we can apply the third equation we learned. Look at A and P as a system. And the conservation, apply conservation of momentum in N direction. So right before impact, what is the momentum of before impact? We have mp, the speed of p before impact, it's vp2, all right? And plus, we have block A, the speed before impact for block A, let's call that VA2, but block it was not moving before impact, so that speed is 0. That equals to momentum after impact, which is mp vp3. So that's a new variable. That's the speed of p after impact at position 3. That's why it's called vp3. Plus ma va3. That's the speed of particle, not particle, yeah, block A after impact at position 3. We solved VP2 from the last step, right? So in this equation, we only have two unknowns. One is VP3, another one is VA3. We have two unknowns but one equation. That means we need one more equation. We can get that equation from the coefficient of restitution. Remember that equation has a negative sign. And the definition of that equation is all the velocity after impact, the difference of all velocity after impact divided by the difference of velocity before impact. And those velocities are only on n direction. So we have Vp3 minus Va3 divided by Vp2 minus Va2. Since we know both particles stick together, that coefficient E equals 0. So that's another equation. We can easily get the conclusion from that equation, which is Vp3 equals Va3. That makes sense because both particles stick together after impact, then they should travel at the same speed. That will reduce our variables to 1. So we are able to just use this equation to solve for the speed after impact. So we can solve Vp3 equals Va3 equals, solve this. What is Vp3? That equals mp Vp2 divided by p plus ma. Okay, any question here? Remember, this is part 2, step 2. We analyze the position 2 to position 3. That's an impact problem. The goal is to find out what is the speed of block A and particle P after impact. And this Vp3 and Va3 are the speed after impact. You get it? And we're done with this step. Now let's look at the last step. It's from position 3. Let's call it step 3. We're looking at position 3 to position 4. Let's go back here. Position 3 to position 4. That's when we have both particle P and block A moving to the right, compress the spring. And we want to figure out what is the maximum deflection in that spring. So this is a pure work energy equation. Go back here. So this is work energy problem. And if it is work energy equation, we have to list all the tables, right? So here we have start with kinetic energy table, T1, T2. Since here we have two masses, we have mass P, mass A. We have to look at kinetic energy. One thing I want to change here, instead of call this T1, T2, here should be T3, T4. We're looking at position 3, position 4. So what is the kinetic energy for block M for M and P? That's a speed we just know, right? Vp3, Va3. That's a speed you need to use to calculate kinetic energy. Just 1/2 mp Vp3 squared, 1/2 ma A3 squared. That's a kinetic energy. What is the kinetic energy at position 4? When the spring is at maximum deflection. That's 0 for both P and A. That's our first table. The second table should be the potential energy at 3, potential energy at 4. In this case, we have different types of potential energies. We have weight force from A, weight force from P, and the spring force. Okay, whenever you do potential energy, make sure you define where's the zero reference level or zero reference point. In this problem, we can still use that right line, which is the zero reference point for all the potential energies. And since we're looking at position 3 to 4, it's right on our zero potential energy reference line. That tells us we should have zeros in our table, right? Zeros, 0, 0, 0. There's no change of potential energy from gravity, from position 3 to position 4. But now let's look at our spring. Spring at position 3, what is the potential energy in the spring? 0, it's uncompressed or unstretched, so 0. At position 4, it's compressed at its maximum deflection, so potential energy is calculated by 1/2 K delta X squared. That's the equation to calculate spring potential energy. Okay, we're done with potential energy. One last table is work done from 3 to 4 non-conservative forces. In this case, even we could have a normal force, but it's perpendicular to the motion of the particles, so there's no work done from non-conservative forces. All right, now we have all the tables set up. We can apply work energy equation. T4 plus V4 equals T3 plus V3 plus U3 to 4 and C. Okay, substitute everything into T and V. We're able to solve for delta X. So the symbolic solution for delta X is MP divided by square root MP plus MA square root 2GH divided by square root Okay. So this is a symbolic solution for delta x, which is the maximum deflection in the spring. And if you plug in all the numbers, if you want to know the numbers, it's around 1.155 feet. Okay. Now you can grade yourself to see how much you earn from this fake quiz, right? And did you answer all the questions? You have all the questions, right? Right before we went through this problem. Now, do you have answers to those questions? Okay. If you're still confused about something, you need to come talk to me. I can help you out. But I hope you learned something from this practice today. All right, that's all for today. I will see you on Wednesday.